Hello everybody, and welcome back to an introduction to machine learning for absolute beginners. This is unit 2 and we are going to cover supervised learning, and we're going to dive into the details of what this entails and actually talk more about the math behind supervised learning and some of the applications, how to actually implement it in your work. And this again is presented by EDU Onyx. So let's go over a quick overview of what we're going to do in this unit. In Unit 2, we're going to have 6 videos, this being the first, just a brief introduction to supervised learning. Some of this information we covered in the past unit, so it'll go pretty quick. In video 2, though, we'll really start getting into more details, and we'll cover linear methods for classification, and we'll talk about filtering and feature extraction, as well as learning multiple classes. In video 3, we're going to apply that to regression and cover the linear methods for regression. We're going to talk about linear regression models and least squares minimization. Video 4 is on support vector machines, where we're going to cover the support vector classifier, kernels, and flexible discriminates. Video 5, this is an exciting video for me. This is on basis expansions and regularization. Most of the time, linear models, such as the ones we're covering in video 2 and 3, are going to be too simple. It's highly unlikely that the true function f of x is actually linear over our inputs. This is just a convenient approximation because a linear model is easy to interpret and is the first order Taylor approximation of f of x. In this video, we will discuss popular methods for moving beyond nonlinearity. The core idea is to augment/replace the vector of inputs x with additional variables, which are transformations of our inputs, and then use linear models in this new space of derived input features. So that one will be fun. We'll also cover piecewise polynomials and splines in that, as well as kernel smoothing methods. The last video, video 6, is going to be probably one of the most useful videos, and we're going to talk about actual model selection procedures, how to pick bias and variance, model complexity, and what parameters you should be using in your models. So that's just a quick overview. I'm excited for all of these videos, but let's dive into video 1 right now. So this is supervised learning, just a brief introduction expanding on the information that we covered in Unit 1. So again, supervised learning is inferring a function from labeled training data. For supervised learning, we have both inputs, and we're using those to predict the outputs. For example, we could be given some specific atmospheric measurements today and yesterday, and we want to predict the ozone level tomorrow. Or given the grayscale values for the pixels of the digitized image of the handwritten digits, which we talked about in the last unit, we want to predict its class label. What number is this, or what letter is this? There is a distinction in supervised learning between the outputs. We have qualitative outputs and quantitative outputs, and this distinction has led to a naming convention for the prediction task: regression when we predict quantitative outputs, and classification when we predict qualitative outputs. So we're going to dive into those in more detail. We'll see that these two tasks have a lot in common, and in particular, both can be viewed as a task and function approximation. And that is why supervised learning is inferring a function. These are really function approximations. So let's get started with the simplest case, learning a class from its positive and negative examples. After this, we're going to generalize and discuss the case of multiple classes, then regression, where the outputs are continuous. So in this example that we're going to use for our simplest class, or our simplest case, we are going to be trying to learn the class C of a family car. So we are training a machine learning network to distinguish between family cars and non-family cars. So positive examples: family cars, these are going to be your minivans, your SUVs, anything with a high safety rating. On the negative example side, you've got maybe race cars and sports cars. Motorcycles, probably not a family car, whether or not you consider that a family car. Either way, we have positive examples and negative examples, and we're going to use these to teach our algorithm how to detect or determine the class C of a family car. So let's dive into the input representation. The inputs are going to be a very essential part of this network. We had a group of experts get together, and they decided price and engine power are the two determining attributes for a family car. There could be others, such as color, safety rating we mentioned, maybe the amount of storage in the trunk. some of those things are going to play a factor. However, we're only going to focus on these two inputs here. So we have x is going to be a vector of x1 and 2, where x1 is price and x2 is engine power. So we're going to start using some of that linear algebra notation as we dive into this example. We also have r, which is a vector as well, 1 if x is a positive example and 0 if x is a negative example. Most of these inputs, in most cases, are going to have binary labels to the classes or example spaces. So instead of saying positive example, you'll just say 1, or negative example is going to be a 0. So in our input representation, each car is going to be represented by an ordered pair x and r, where both x and r are vectors, and the training set is going to contain n such examples of these. So we could have any number, the more the better. This is machine learning, so large data sets are going to be more beneficial just because of probability theory. However, that number is undefined here, but we can write our entire input as this capital X is equal to x of t, r of t, summed from t equals 1 to n, where 1 to n is just going to be an ID for our different inputs. So again, x here is a vector and it contains both x1 and x2, and then r as well is going to designate 1 or 0 depending on a positive example or a negative example. So this is our input representation. From here we can move on to the development of a hypothesis class. So again, the same group of experts gets together and they say a family car is going to have a price between P1 and P2 and engine power between E1 and E2. They decide that this might be a reasonable way to classify a car as a family car if the values fall within a given range. Note that we do not know the specific parameters yet. So the training data can be plotted in the two-dimensional space where each instance is a data point at coordinates x1, x2, and its type is given by r. This is called the input space. We mentioned input space in Unit 1 a couple times. This is what we're talking about. Again, we only have two inputs, so our input space is two-dimensional, which makes it simpler for us to look at. So we have our shaded box in the middle here, and this is just showing our potential hypothesis class. Note that we don't actually know the values of E2 and E1, although it's depicted in this graph as such. But in our hypothesis class, we would not know that yet. However, we're going to use this class to find the actual hypothesis h of x, which would have distinct values of E and P, to approximate C, our class of family cars, as closely as possible. The experts define the hypothesis class. However, the parameters are not known until we actually train this algorithm. So here is our hypothesis class. We are predicting that this is a reasonable way to classify C, a family car, and to determine that class. However, we haven't determined the specific hypothesis from our hypothesis class yet. Notice that there would be any number of hypotheses because there would be an infinite number of P1 and P2 and E1 and E2, since these are just numerical. These variables are numerical and they could be any number at this point. However, they are going to take shape when we actually use empirical error to train the network. And the empirical error is the proportion of training instances where predictions by our hypothesis h of x do not match the required values given by the input x. So again, we need to find the values of these four parameters given the training set to include all of the positive examples and none of the negative examples. So here our hypothesis h of x is going to be 1 if it classifies it as a positive example, and then 0 if it's classified as a negative example. And our empirical error e, given our hypothesis and our input data x, is going to be the summation of all of these over all of these data points, t going from 1 to n, of this function L, which is 1 if a does not equal b and is 0 if a equals b. So if our hypothesis h of x for a specific point t is equal to r, then we get 0 for our empirical error, or for the error for that specific point, and we get a 1 if these values do not match. And then the empirical error is going to be the total summation of that. And this is actually what we are trying to minimize. So we would pick 4 values for our parameters, our range of values for engine capacity and for price, and then we would calculate the empirical error and use gradient descent to actually find a local minimum and minimize this error using the multivariate calculus. So this is pretty simple for this the simplest case scenario. However, it's helpful to look at some of the math that's actually being used behind this and some of the things like the hypothesis class and the input representation. So when our algorithms do get more complex, it's easy to understand where some of these terms are coming from and how the algorithms are actually structured. So moving on from empirical error, the next step would be to actually use our algorithm, and that is going to bring in the concept of generalization. How well our hypothesis will correctly classify future examples. Because we don't care if the algorithm does very well on the training set if we're not able to use it in the future on unknown data points. So generalization, or how well the algorithm generalizes, is going to be talking about how well it can do on additional data that wasn't a part of the training set. Sometimes you can train algorithms that will learn the training set very well, but they'll actually overfit the data and won't generalize to new inputs. That's going to bring in the most specific hypothesis, S, which is going to be the tightest rectangle in our case, since it's 2 dimensions. That includes all the positive examples and none of the negative examples. Also, we're going to have the most general hypothesis, the largest rectangle that includes all of the positive examples and none of the negative examples. And building off these 2 terms, we're going to get doubt, a case that's going to fall between the most specific hypothesis and the most general hypothesis. Sometimes, if we have a case of doubt, we want to not classify the data point, but instead return something like uncertain or unknown, so that the user can look at that case specifically and make a determination. Classifying a family car as a non-family car isn't going to be too bad, but in some situations we really can't have our algorithms misclassifying data points. So these are just some other good terms to know on top of the hypothesis and hypothesis class, as well as our input and input representations. We also talked about input space. And again, this was just a brief introduction to supervised learning. Hopefully this was a lot of the same information from Unit 1, but with a little bit more detail on the math and some more of that. In our next video, we are going to talk about linear methods for classification. So we're actually going to get a dive into how we use that empirical error. And we'll talk about filtering and feature extraction, as well as learning multiple classes instead of just one class, like in our example, the class of a family car. Thank you for listening, and I will see you guys soon in the next video. Thanks.